So if you're naming an ionic compound, you certainly want to be able to identify what the metal is and non-metal. Now, the one that you should make specific note of is if it happens to be an ammonium, that's the only one that would not have a metal. It might have an ammonium and then follow with a non-metallic element or polyion. And it breaks down into binary ionics. And a binary ionic is two different elements, but it may have more than two atoms in the structure. I can give you an example. Sodium chloride is a binary ionic compound. Sodium being a metal, chloride on the halogens is, of course, non-metal. But if you have, say, aluminum chloride, its formula will be this. Now, it's got 3 chlorides and an aluminum, which is 4 atoms or elements in the structure, but it's still just 2 different elements. So when we talk about binary ionic compounds, 2 different elements in the structure. And again, be wary of the ionic ammonium structure. So that is the uniqueness of that compound. Okay, in naming these, you have to be able to break them down into just the simple binaries like this, or polyionic structures, as well as including oxidation states. Now, you need to review what are the what are the fixed charge elements. So going back for just a second and looking at fixed charge elements before I do this, remember group 1 is +1 all the way down, including hydrogen if it's. Now there are hydrides in which it has a -1 charge. We'll get to that. +2s all the way down. And then you come over here, fixed charge -1s primarily. The acetine is a metalloid and typically not included in the halogens reactions for the most part. And then zeros for that one. Then you recall, if you got to find silver in this set, it's always 1 block +1. And then +2 metals, zinc and cadmium, 2 blocks. And then aluminum, gallium, and indium are always +3s. Sorry, stop right there. +3s, 1, 2, and 3 blocks. Now that's circumstantial, not scientific, right? It's just a memory device. Over here, tantalum is a +5. Then you have +4s, and then +3s. So really what you're looking for in your periodic table to help you remember those transitions that have fixed charge is silver and tantalum. Starting with silver, left to right, +1, +2, +3. Now tantalum always is a +5, you have to remember that, but you count 1, 2, 3, 4, 5 from left to right. And so that kind of fills in the rest of it. Okay, so if we have a fixed charge, you don't have to put any special notations in. For example, here, sodium chloride. Sodium is always a +1 and chloride is always a -1. You won't need anything special for the halogens or negative structures, but the cations can either be fixed charge or variable charge. What if you have copper chloride like that? There are 2 forms of copper, a +1 and a +2, And both of these compounds exist and are valid. So writing the nomenclature for this, it says for the, I'll move this out of the way, for copper chloride, this is a +1 -1. How do you know? Well, chloride's a -1 fixed charge, so if that's, you assume this is the correct formula, that has to be a +1. Well, there's also copper chloride subscript 2. Well, chloride's still a -1, and it takes 2 of them, so you have to have a +2 over here to sum of charge equals 0. So the deductive reasoning is logical here, but how do you name these to separate the two? You put it in parentheses, Roman numeral in parentheses, it defines the oxidation state of copper 1 or copper 2. Now you just write out the chlorine as a chloride if the element on the end is by itself. In other words, you have copper and sulfur here, it'd be copper sulfide. The IDE ending indicates that there's only one of those elements at the end of the formula. Here, you put copper 2 chloride, regardless of whether there are 2 of them or not. But in order to define the difference between the 2 ions, you have to put in parentheses what their oxidation state's in. Now, you ask, how do I tell what the oxidation states are? Well, you either determine it from the given formula over here, +1 +2, sum of charges being 0, or you determine it from the nomenclature, because they have to put when you write a nomenclature, you have to put the oxidation states in parentheses, or else, it doesn't mean anything in terms of writing the formulas. So that's the first part of the issue on binary structures and so forth. Let me get to and it's very straightforward on the polyions also. If you have a potassium connecting up with a nitrite, for example, 1-to-1, and you have a KNO2. Well, this compound will be potassium nitrite. You do not have to put in parentheses the oxidation state of the metal because it's in group 1 and is a fixed charge element. However, if you have a variable charged element, cobalt plus the nitrite, like that, and you hook up the cobalt nitrite like that, you have to know what that oxidation state is in order to know how many you have here. Cobalt comes in +2s, +3s, I think +6s, but let's say you have to have that +2 in there, so you have a -1 and a +2, so you have to have 2 of those, and so it'd be like that. Now, in naming this, since you have a cobalt +3 plus a nitrite, to give a cobalt NO2, and then you'd have 3 of them in that case. Well, in order to identify what the cobalt is, you have to put the oxidation state. The sum of charges equals 0. That has to be a +3, and that one has to be a +2. Well, this one is cobalt 2 nitrite. Whereas the second one is cobalt 3. Like that, and of course you're supposed to memorize the polyions, know them by heart, and you know the ITE endings like that. So in variable charged metals, you have to put them into parentheses. which are in the polyion structures. In the polyion quiz, you had an OCl minus in there. That's a hypochlorite. And then you had an OCl2 and OCl3. That's a chlorate. This is chlorite, chlorate, and perchlorate. Like that. Well, you can also have OBr in the same halogen series, and that's why we call it an analogous. They're similar. And iodide also. So in naming the first set over here, I'll come down here, and this is starting at the first one is hypochlorite, and then you go to chlorite, and then chlorate, and then perchlorate, like that. But you can do the same thing with this second set as hypobromite. And bromite, chlorate, bromate, excuse me, and perbromate. And easy enough now. Hopefully you see that it's iodate or iodite in the nomenclature. And so that's why we call these analogous series or similar series in their nomenclature. So these are negative particles, and all you have to do is put them with a positive particle. Some charges 0. If you put sodium in front of the OCl, it's sodium hypochlorite, and that's the primary component in laundry bleach. And so you have, if you put a sodium on this one, it'd be sodium chlorite, and then the third one, NaOCl3, would be sodium chlorate, or sodium bromate, or sodium iodate. And so the issue is, while you know one, you also know two others just substituting the halogens into the system. Still have to put in the parentheses the oxidation states followed by the polyion. So if we had a nickel plus 2 combining with ClO3 minus, like that, to give us nickel chlorate, you'd have to have 2 chlorate ions in there, but you would have to identify the oxidation state of nickel. It's basically, it doesn't matter whether you know it's a variable charge or not. It's not a fixed charge. If you know the fixed charge from the periodic table, you'll see that one's not a member of the fixed charge set. And so you have to put that oxidation state. And so it's easy to name them from that perspective. And same way with any others, any other polyions. You name the metal followed by the non-metallic component, and be sure to put the oxidation state in there if it's a variable charge. How do you know it's variable? It's not a fixed charge, and you're supposed to study the periodic table and learn which ones are fixed charge, like that. Nomenclature, especially in the molecular compounds, comes in what we call common names like water and ammonia, and then there are systematic names. And we don't call water hydrogen oxide. but it is a systematic name. And the systematic names are based on what we call the IUPAC system. International Union of Pure and Applied Chemistry. I'm not going to ask you that on a test or anything, just FYI. Like that. So, when naming molecular compounds, we have certain rules also that are shown in the handout. We have binary molecular compounds that are broken down into no hydrogen type structures and then hydrogen type structures. And I'll lay this out to you. And then we have what we call molecular acids. It's very important that you spend some time learning how to name molecular acids because they make up a significant portion, especially of Chem 2, as you get into acid bases, theories, and equilibrium. And we'll go with the no hydrogen first. Okay. In naming these, you see how I've got it couched in here. It simply name the first element with a prefix if it's more than one, and then follow with the element with an IDE ending indicating that it's by itself. For example, if we have CO and CO2, these would have single elements in the first position. So we name them just carbon, but the second one is a single element and we put mono on it, monoxide. Same way here, since you have two oxygens, it's carbon dioxide. The point of issue is that I'm making, if it's just one element, you don't put a prefix. And of course you see the prefixes, I think I've put them up here, that you would use. You don't name CO as monocarbon monoxide, and you never hear CO2 named monocarbon dioxide. So it's just simply a single structure. But if you run into something like N2O5, where there's more than one of the first element, then yes, you have to use the prefix designation di, or if it's three of them, tri, tetra, penta, and so forth. So if N2 would be dinitrogen, indicating that there are two nitrogens in this formula. Pentoxide. So the di and then penta are required in that naming of that formula. So these are hydrogen containing binary molecular compounds, and to identify these I want to kind of make a periodic table of sorts in this. We're going to start with group 4, then 5, 6, and group 7. And under this we'll start with carbon and silicon, and 5 is nitrogen and phosphorus. We'll go ahead and put the arsenic in there. And then group 6 starts, of course, with oxygen and sulfur, and comes down selenium and tellurium. And then you have the fluorides, chloride, bromide, and iodides like that. Now, each of these we look at them as negative. This is a -4, -3 oxidation, because this is 5 plus 3, and this is a -2 oxidation. This is -1, as we've been talking about. Now, hydrogen is always a +1 until I tell you different. Oxygen is always a -2 unless I tell you different. So if we take hydrogen as a +1 oxidation state, how many hydrogens would you need to neutralize 4 negatives? Well, 4. And so we put 4 hydrogens on that. Here, same way with silicon, it's a +4, so we need, a -4, so we need 4 plus charges, and so forth. Here, we need 3 hydrogens to neutralize 3 negative charges, and then like this. And then here, now here's where it's interesting. The common notation for the formulas, molecular formulas, finds the hydrogen on the right side in groups 4 and groups 5. You see carbon followed by hydrogen. CH4 is methane, or silane, SH4. Ammonia, you recognize, is an NH3. But when you get over here and you need hydrogens to neutralize the -2, you put it on the left side. You don't read water as OH2, you read it as H2O. And so that's kind of an interesting trivia point, but it is the common practice. Same way here is H2S, hydrogen sulfide, and so forth. And here the hydrogen goes on the left again. So it's just a little notation. Once you get into the group 6, group 7s, hydrogen go on the left, but when you start out with group 4 and 5, hydrogen's on the right of each one of them to neutralize the oxidation state of each element. Okay, so we have 2 types of nomenclature here, a common name and a systematic name. Common names like CH4 and SiH4, this is methane, and this is silane. So, it's just as accepted nomenclature in the chemical community. Here in H3, common name is ammonia. We don't call it nitrogen hydride or hydrogen nitride. Here, of course, that's water. We don't call it hydrogen oxide, and so forth. Now, all the others have systematic names. Once you get past these 4 nomenclature common names, the way you name the remaining structures is you say hydrogen followed by the anion with an IDE ending. So this would be hydrogen phosphide. And as I mentioned earlier, if the IDE ending is attached to the nomenclature, it means there's only one of that element there. And you can see that easy enough. And naming this one, that's arsenic, so it's only one of them, so it's hydrogen arsenide. Like that. So the IDE ending just says, well, there's only one of those in the formula. And here is hydrogen sulfide. And of course, hydrogen selenide. So it's some common denominators, you might say, common trends in the nomenclature formats that are here. Now, when you get to the hydrogen halides in general, there are 2 designations. Sometimes these are in water and sometimes they're not. If they're not in water, they will be gas phase. You'll see a G, and there are reactions that take place, and the byproduct of that reaction is one of the hydrogen halides. If that's the case and they're not in water, you call them hydrogen fluoride, just like you did with the others in this systematic process. So that would be hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. However, if they go into water, they become acids. An acid requires water and ionization. If it doesn't ionize, it ain't an acid. Okay, if it doesn't have hydrogen, it's not an acid. Well, it depends on the theory you're working with. So I'm going to come down here and put these in down here. If hydrogen halide compound is in aqueous solution, then name as an acid. So if we have HF, HCl, HBr, and HI, to designate them in water, we put after the formula an AQ. And I haven't mentioned S is for solids, and L for liquids, and G we just saw is for gases. But here is AQ, meaning that the primary solvent in the solution is water. If they're in water, then this is called hydrofluoric acid. Instead of hydrogen fluoride, it's hydrofluoric acid now. And you recognize this one probably, hydrochloric acid. And hydrobromic acid. And hydroiodoic. So I know this is a lot of little pieces and parts, but it's very important that you separate and be able to deal with it. Because as we get deeper into the course, we'll be looking at these and talking about them in terms of their nomenclature as well as their formulas and solutions that they're in. Okay. Molecular acids with polyions. The polyion that we're working with are broken down into the endings. As you see, they're either given in an ATE ending or an ITE ending in the nomenclature of the polyion. If it is an ATE ending in the polyion, you change the polyion ending to "ic" and then stick the word acid onto. So IC acid. Now I'll give you several examples. If it's an ITE ending in the polyion nomenclature, you change it to OUS, OUS acid. Now there's some slight variations here, but I think you'll be able to manage this. For example, if we start with NO3, okay, this is a nitrate ion. So if it as an ATE ending, it wants to go to an ic acid. Now the acid must have a hydrogen on it. So how many hydrogens do we need for one negative charge? Well, of course, one. So the acid would be HNO3, and since the polyion has an ATE ending, this is called nitric acid, like that. If you have an SO4 negative, like that, that's the sulfate, -2, excuse me, sulfate ion. So the ATE ending would make that an ic acid, so that'd be sulfuric acid. Like I say, it's a slight variation, but I think you can handle that. So you change it to the ic acid if it's a sulfuric acid, it's an H2SO4, so that it neutralizes the two negative charges that are in the polyion. Now over here, if you're in using anions that have negative charges and ITE endings, NO2 is a nitrite. And so the acid would be HNO2 and is called nitrous acid. So you see that OUS ending is applied to the nomenclature. Here is SO3 minus 2 will give you H2SO3. And since that ends in a sulfite, that's a sulfurous acid. Like that. So you can go down through all of your polyions and neutralize the negative ions, that is, with the appropriate number of hydrogens. And then if it's an ATE ending, you just name it relative to the ic acid, or if it's an ITE ending, it's OS acid. We'll give you some more examples on that. So let's do this one. 3 hydrogens plus a phosphate minus 3 gives you H3PO4. Since that's a phosphate, how do you name the acid over here? It's an ic acid at the end of it, so that'd be phosphoric acid. See how the difference is? Now you have to know your polyions to deal with this. That's why I give that polyion quiz, hopefully to motivate you to dig into those nomenclature terms and learn them. Here's one, H plus C2H3O2 minus, and this is an acetate ion. And so if we neutralize, it's only going to need 1 on the acetate, so it has an ATE. What would it be? Ic acid, so it'd be an acetic acid. Going through some of the analogous series, here we have ClO like that, and we'll go to HClO, and this is a hypochlorite. So then the hypochlorite, when you neutralize it with a hydrogen, HClO, and ITE becomes what? OS acid. So this is hypochlorous acid. So all you have to do is, know your nomenclature and apply the appropriate ending to the nomenclature of choice. How about so it was one of those analogous series things, and that is a bromate. And so it gives you HBrO3 is the acid formula. And so that ATE becomes ic acid, so it's bromic acid. If it was a BRO, just 1-to-1, it would be hypobromous acid. So you can see the common trends in the naming of these compounds. If you just a little bit of study in there, you master it pretty quickly.